Hello learners, this class is for second year of B.Sc second year of physics. Paper name is optics, 4th sem. The chapter name is interference and today's topic is oblique incidence of a plane wave on a thin film due to transmitted light, or known as cosine. Now you can see the diagram over here. Now I'll explain you the diagram, you can easily understand the theory. So here we are having reflections and refractions, and two transmitted rays are there. Okay, so till here we have seen in the reflected light answer also. Okay, this is for transmitted light, this is for transmitted light. The previous video we have discussed for transmitted light also, reflected light also. So oblique incidence of a plane wave on a thin film due to reflected light, that we have seen in the last video, and this video is of transmitted light. The transmitted light means we will not the phase will not change. Okay, abruptly, it will not suffer any change of pi. So you can see the diagram here. So this CT and ET1 are the two transmitted lights that are emitting out of the surfaces after being, see, this is the illuminated light, it's being transmitted like this, and again it will take internal reflection. Okay, and again take internal reflection like this, and it will transmit outside. So this CT, this CT and this ET1 are the two transmitted rays. So these rays have originated from the same point source, hence they have a constant phase difference. No zero phase difference or constant phase difference is there. Okay, that means they are having a sustained interference. So we are going to find out the path difference between these two transmitted rays. For that we draw normals, like we have drawn for the reflected rays answer also. Okay, we draw normal CQ on EP. Next we also draw DE, right? DE. One second, wait, we draw normal CQ on DE. This is our DE. Okay, CQ normal is drawn on DE, and EP is drawn on CT. Okay, we also produce ED. We also produce ED backwards like this. So this is about the diagram. We have to see the path difference between these two transmitted rays. Okay, that's what written here. You can see, due to simultaneous reflection and refraction, we obtain two transmitted rays CT and ET1. These rays have originated from the same point source, hence they have the constant phase difference or zero phase difference, and they are in a position to produce sustained interference. When they are combined, they will produce a sustained interference. So we have to calculate the path difference between these two transmitted rays, CT and ET1. So for that we draw normal CQ on DE and EP on CT. We also produce ED in backward direction. We'll take it backward direction where it meets CF at I. Okay. Now we have to find out the path difference. So the effective path difference is given by del is equal to mu CD plus DE minus Cp of refractive index of the air 1. Okay, and from Snell's law we know mu is equal to sin I by sin R. Now see the diagram for triangle CPE and triangle CQE. We get sin I as this one and sin R as this one. CP by CE and sin R as QE by CE. CEC cancels, mu is equal to CP by QE. So we can write that as Cp is equal to mu QE. Let that be equation number 2, and substitute in first equation, that is del is equal to mu CD plus DQ plus QE minus mu QE. Mu taking common, we get like this, and QE cancels, CD plus DQ. From the diagram, CD plus DQ can be written as QI. So that is del is equal to 2 mu T cos R. So this QI is nothing but, you can see here, from triangle CQI, we can write cos R as IQ by CI. IQ by CI. So from that, IQ is equal to CI cos R. CI cos R. So IQ is equal to 2 mu T cos R. This is the equation. Here, it should be remembered that inside the film, reflection at different points take place at the surface backend, but by rarer medium. So no abrupt change of pi takes place here. No phase change is there. The maximum occurs when effective power difference is n lambda, and the minima occurs when effective power difference is 2n plus 1 lambda by 2. That is 2 mu T cos R is equal to 2n plus or minus lambda by 2n plus or minus 1 into lambda by 2. So film appears dark over here. So thus the condition for maxima and minima is in transmitted light are just as the reverse of conditions for reflected light only. But not phase change is occurring, but phase change of, it doesn't suffer the phase change of pi in transmitted light. Okay.